Good evening, good afternoon, or this is the second edition of Helping webinar under Hydrologic Design, Solutions and Communications. Currently, we have two subgroups. One is floods and the other one is drought and water management. Now, we will be listening Fabrizio Fenicia, thanks to him for his contribution about advancing hydrological predictions, data, information extraction, and modeling insights. He will talk about this topic and we will have some time for questions. So the stage is yours, Fabrizio.
Okay.
You can share your screen.
Cochrane, thanks. Hello, everybody. I'm gonna share my screen now. 1 second. Do you see the presentation okay?
Yeah, everything looks good.
This presentation is going to be about advancing hydrological predictions, data, information extractions, and modeling insights. First, I have a slide about who I am. I'm a group leader in hydrological modeling, and I work at EAWAG, who is a water research institute based in Switzerland, near Zurich. And I work primarily on models, on data, and on understanding catchment behavior. I thought about starting this presentation with an equation which probably you haven't seen before because I just made it up for this occasion. And it is a conceptual equation that says that our ability to make catchment predictions depends on data, on our ability to extract information from the data, and on the models in this order. That's why I made the D larger and M smaller. So data are time series, of course, like hydrographs or maps of land use. We typically need to represent this data in a compressed form. So, for example, maps we represent through indicators. If you think about topography maps of like indicators like elevation or average slope, but there is much more in the map than these indicators. Therefore, becomes important to represent them in a meaningful way. And of course, when we talk about hydrographs, you heard about hydrograph signatures and the importance of signatures in various applications. And then we have the models, which I put at the end because they come at the end of this chain. And I put it smaller than the other because I think that perhaps, especially with the advent of machine learning models, we have probably reached the limit in terms of predictive performance. And therefore, if you think about improving, then it's perhaps wiser to invest on the other aspects, such as on data or on our ability to extract information from data. And in the rest of the presentation, I will show you some examples about that. So in the past, sharing data and, by the way, also models was not very common. Here it's a picture about fieldwork in Luxembourg. I started my research activity working in Luxembourg in back then the Lippmann Institute, and the data belonged back then in the early, at least till the early 2000s, belonged to who collected it, and not only the institution but really the person who collected it. And you really had to be a good friend of this person if you wanted to have the data. And also models. It was very uncommon to to have available open source models. For example, I started to work with the HBV model, and here on the right you see the manual of this model that I received. And not only you got the executable of this model, but also this model had a hardware lock. It was a key that you had to put on the back of the desktop computer to ensure that you would not be able to use this model in parallel on multiple computers. And now things slowly, today things are very different, things have changed, but not even so recently. For example, this FAIR guiding principle paper that now everybody mentioned is from 2016, and the first CAMEL dataset is from 2017. So it's really about a decade that things have started to change. And we, with our research group, we followed these developments. And here you see 3 data papers that came out of our group. This is CAMEL's CH. CH stands for Switzerland, from Marvin Hoge. And then there is this paper on scientific data about CAMEL-CH chemistry. So it augments the CAMEL's data set with water quality data. And this is a paper also on scientific data. It's called eStreams. And it groups together all available stream flow data that is in Europe. And so the problem is that this was from Tiago Nascimento. And the problem, and also, by the way, this chemistry was for Tiago. The problem is that this data, you cannot redistribute them. So we could not just copy them, put them in a database and redistribute them. So what we did instead is that we provide links to the data provider and ways to download the source data if you need them. Otherwise, what we are allowed to do is to redistribute some statistics of this data, like monthly averages, for example. And by the way, also from the modeling side, there has been a lot of, now there is much more online. There are a lot of many model codes are available online. And just to present something from our group, this is SuperFlexPy, which is Python code that allows to build reservoir-based models, lumped or semi-distributed. And there is a code, there is a website with several examples. So if you want to have a look, you're free to do that. And it basically implements this principle of flexible modeling, where from some generic elements, you can build different architecture, including some available, some known more famous models like HBV or GR4J and so on. So now spoke about just data itself, now about extracting information from data and some examples about why this is very, very important. So this is the Moser catchment. There are several stations here, and it's a catchment of 27,000 square kilometers. And here all the hydrographs plotted. So one of the first things you would ask yourself if you are a hydrologist is, why are these hydrographs different, right? And so what can it be? It can be the climate, of course, the spatial distribution of climatic inputs, rainfall, temperature, or it can be the landscape. So what you do is you start regressing the signatures of the hydrograph, and so some summary statistics of the hydrograph with the landscape or climate indicators. Now, what's interesting is that in this case, the readily available landscape indicators gave very poor fit to some of the signatures, such as, for example, base flow index. So in order to find a good correlation with base flow index, we had to go beyond what was readily available. Take the lithology map, group all these different classes, lithology classes, into something into relative permeability classes, so something that is hydrologically meaningful. And only when you do that, if you regress the high permeability with the base flow index, then you suddenly find a good fit. So this is about the importance of representing maps in a meaningful way, because maps contain really a huge amount of information, and it's important to distill the relevant one for our hydrological applications. Here it's another case study by Tiago do Nascimento, was recently published. In the previous slide, we used the regional map. So a relatively detailed and accurate map, which we reclassified into these three or four permeability classes. What we did here was to compare what we would get using the same reclassification approach using different available map, a global map and a continental map. So global map means a geology map which is available for the entire globe, and a continental map is a geology map which is available for Europe. And the regional map is a collage of regionally available maps, the one from Germany, the one from France, from Luxembourg, from all the countries that belong to this catchment. And so what we found is that, as we saw before, now there are many more catchments than before, but the regional map provides a very good fit with base flow index, so correlation 0.8. If you go to the continental and then to the global, the correlation reduces a lot. And the reason is that these maps are less accurate, or maybe they have less classes. You can see here that there is a whole entire region of this catchment that is misclassified in the global map. And the reason is that the global map has many less classes, so less ability to diversify. And so the correlation increases with map details. We also separated the larger catchments from the smaller one, just to check whether the reason for this poor correlation was due to the small catchment. Well, in this case of the global map, even if you look at big catchment, you have a poor correlation. Here it improves if you filter out the small catchment, and also here it improves. In fact, in the global map, you have, and also in the continental, you have many catchment with either 0 or 1 geology because of this much coarser classification. So what's interesting is that if you are interpreting catchment behavior, you want to know what are the processes that determine the spatial diversity of all these catchment, the spatial diversity, the spatial variability of the base flow index. Here you have several signatures in this matrix, several signatures, and then what is the catchment attribute that best correlate with this signature. So here we have the best attributes from global geology that correlates to this signature, continental, regional geology, climate, land use, soil, and topography. So if you are interested, for example, in base flow index, and you want to know what causes the variability of the base flow index, and let's imagine you don't have the continental and the regional map, then you would think that probably geology doesn't matter too much, and maybe land use best correlates to base flow index, and then you basically go to you draw the wrong conclusions. if you have the regional map, then it really stands out that geology actually affects the base flow index much more than all the rest. And other signatures may be affected by something else. For example, the average flow best correlates with climate, which makes sense. And also correlates very well with topography, by the way. And then you have to somehow reason what is correlation and what is causality. And so obviously topography, so elevation in particular, is correlated to precipitation because usually higher elevation have more rainfall. So the correlation between elevation and topography and average flow is not a causal relation. It's just a correlation, whereas the causal relation between precipitation and stream flow. Okay. Now,
Okay.
yeah? No, okay, I just heard something. Okay, then you may wonder, does geology matter everywhere, in all catchments, no? So what we did in this paper from Don Nascimento was to analyze many different catchments in Europe. So many like the one before with many catchments inside. And then we analyzed individually all of these catchments. And then we asked the question, what is the landscape or climate attribute that best correlates to base flow index? And we can see that for several catchments, it is land use. For other catchments, it is soil. For other catchments, it is climate. And then there is topography, and then there is geology, and so on. Almost equally distributed. So this tells that basically the spatial variability of catchment is governed by local controls. It's very difficult to find universal, generalizable relationships. And therefore, it is important to look at a region, to perform regional constraint analysis and not to put everything in the same pot. Because in fact, if you look at all the large sample analysis that have been done where all data were analyzed together, what comes out of these studies is that actually climate has a big role in determining spatial variability, but it was not found, the relation between landscape and spatial variability was always very weak. And perhaps this is one of the reasons. So the reason is that these relationships are local, they are not generalizable. So how to represent this understanding that we get from data analysis? One way to do that, which I find particularly useful, especially in view of modeling application, is to represent them through perceptual models. We are in hydrology, we know this concept of perceptual models, but we usually associate it to fieldwork, so to small catchments, to experimental catchments. But nothing prevents us to create perceptual models of large catchments, especially if you have enough data that you can analyze and interpret, such as data at many internal gauges that allow you to make this correlation between stream flow signatures and landscape features and interpret them. So, for example, just to provide some guideline of what kind of questions could this perceptual model could answer. These are some of the questions. Which signatures most effectively characterize spatial variability? Okay. Name these signatures. Name them in the perceptual models. Which climatic or landscape factor controls the spatial variability of this signature and therefore help define distinct landscape units, such as, for example, different geology classes or climate classes or whatever. Okay. What are the dominant processes that operate in each of these landscape units? Can we expect much base flow or more surface flow and so on? How do these landscape units connect to each other? Do they operate as separate entities or they connect one to the other in some way? Can we say something about the relative magnitude of the processes that operate in these units, which are faster than others, slower than others, and so on? And all these things then translate into very useful information when we are going to build a model. That's why I say the model should come at the end of this chain, because if we do all this analysis beforehand, we are half done with the model and with informing the decision that developing a model requires. No? So, for example, signatures can go to the model evaluation, the spatial controls then become automatically hydrological response units, the dominant processes translate into the model structures, and then the connection and parameter constraints, all these things we can already inform them. So now this is schematic taken from another paper, not mine, from Feng, WR 2022, which represent a typical regionalization approach. How does it work? So clearly now in hydrology, we are not looking anymore at individual catchments. This was the past. No, now we are much more interested in extrapolating what we can learn from one catchment to another in regionalization. So a typical regionalization setup works like this. We have a regionalization model that takes as input the meteorological variables and the landscape attributes and informs the parameter of the models in different catchments. So depending on the variability of the attributes or of the meteorology, this will vary. Now, the ability of the quality of the prediction generated by this model heavily depends on what you're going to put here. So on the attributes, on the meaningful attributes. And that's why I say that extracting information from the data is very important. Because if you don't have the right attributes here, you cannot hope that this model will regionalize well. Okay, so now this is another study from our group, which is about how many signatures you need to represent a hydrograph. And this is a strange setup, if you want, because the setup of this model is we have a hydrograph as input, and we want to predict as output the input. So we want to predict the input to this model. So this is something, I mean, in principle, very wrong. No, what you if you put as input the output that you want to predict. But what happens inside this model is that this hydrograph is compressed into a few numbers. 1, 2, 3, or more numbers. You see them depicted here, the numbers, the dimension through which this hydrograph is compressed. So we asked, so we have the hydrograph, we compress it into 1, 2, 3, or 4 numbers. Then we have the meteorology, so the precipitation and so on. We feed it into this model. We put in as input these 4 numbers that we, or 3 or whatever, that we extracted from this hydrograph, and we want to reconstruct the original hydrograph. And then we test, we fit this model to reproduce as good as possible the input, and we try to figure out in this way what happens when we increase the number of the dimensions of these so-called latent features. And here you see the results. So we have 1, 2, 3, 5, and 27. So what we see here is that above 5, dimension 5, there is not much improvement in reconstructing the original hydrograph. So this tells us that the hydrograph, you can really compress it into 5 numbers, not more. And this aligns with the finding that we already heard, that the complexity, how much complexity is warranted in hydrological modeling. You know, more than 5 parameters usually is difficult to estimate from rainfall runoff data alone. Then another thing we did was to, instead of putting here the information extracted from the hydrograph, we put the landscape feature directly, and then we see how good can we reproduce the original hydrograph. And you can see that if we inject the landscape feature directly, which is this first bar, we are between 1 and 2. And this tells us that these landscape features are really not so very informative of the landscape features that matter. Okay, so there is really much to do in extracting landscape features. There is much to improve, much to gain in researching which landscape feature actually would matter and would help representing the landscape in a meaningful way. So then you ask why available catchment features are not so informative. And the reasons may be, of course, it could be that they are uncertain. Of course, all these maps are uncertain, and statistics from this map are uncertain, especially the soil maps, the geology maps, as opposed to the topography, which is, let's say, more accurate. They may have limited informativeness, so we may use landscape indicators such as elevation or a slope that are not really what matters in the end. And another reason could be what I said before, that spatial variability, so that because the relationships between landscape feature and signal, they are spatially variables, it's difficult to develop a unique relation which is valid everywhere. And this could prevent the usefulness of this map. These are all things to further investigate. So, as I said, so one important thing to mention is that we need model to make predictions. You cannot make predictions without a model. So then why I put the m small n at the end? One reason is because you are probably all familiar with this plot, LSTM model. Probably already set the limit, the maximum that we can do with modeling. And another reason is, as I said before, modeling should come at the end of a data analysis process. If you have done the data analysis process well, then you can inform the decision of a distributed model, such as how to break the landscape, how to model each unit, how to connect them. And now, to skip the data analysis and just do modeling and compare in blind way thousands of models is very computationally expensive. That's why it's important to tailor the hypothesis as much as possible and to the minimum possible. And to give you an example, of how models can be used to test hypotheses. This is a recent work from Pasquale Perrini from the Polytechnic of Bari. What he did was to look at a catchment in Italy, where we have, he concentrated on 3 gauges, 2 headwater catchments, and 1 outlet. And as usual, as in the Moselle catchment, we just look at the hydrograph and we ask ourselves, are they different? Why are they different? Okay, what can explain the differences? So what he did was to look at the runoff coefficient for different events. And what he noticed is that for the outlet, the runoff coefficient increases continuously, whereas for the headwaters, the runoff coefficient goes up and then reduces. And then the question is, how can you explain this different behavior? These are, you can say, signatures also of catchment response behavior. And we want to use these signatures both to develop our model and to develop our model hypothesis, as I said before, but also to test that our model is actually able to reproduce this behavior. So if you know the model theory, well, most models are based on variable source area theory. So this theory suggests that if the catchment becomes wetter, the runoff coefficient has to increase always. So it's clear that if you use traditional models based on variable source area, even without trying, like top model, HPV, GR, Xinjiang, and so on, even without trying, you won't be able to match this behavior of runoff coefficient going up and then down again. What you need to do is to implement additional process. So what can it be that causes the runoff coefficient to go up and then down? Well, what it could be, the hypothesis is that it is not saturation excess flow, but it is infiltration excess flow. So it could be that the rainfall intensity is actually driving this process rather than the catchment wetness. And this motivated different model hypotheses: Hortonian, Danyan is variable source area, saturation excess, a mix of the two, and so on. And these comparisons between models allowed to distinguish different contributions for different events. So the first event was Hortonian overflow dominated, the second two were mixed, and the last event was mostly surface, mostly saturation excess flow. Not only temporally, but also spatially, so that headwater catchments had different processes than the valley, basically. So when you use models for interpreting catchment behavior, first of all, I would say it's very important. One of the main uses of models is to interpret catchment behavior. And the reason is that when we study catchments, we know the inputs, we know the output, we know nothing. We know nothing about what happens in between. And so the models allow us to reconstruct what happens in between. And we can use this to interpret basically these intermediate processes. But we have to do it carefully. And here we wrote a paper with Dimitri Kavetsky about modeling guidelines, and in particular about the importance of comparing models to a basic benchmark null hypothesis, the importance of doing stringent validation, perhaps not just time validation, but space-time if possible, and also the importance of comparing models in a controlled way. So models that differ in one aspect so that we can attribute the difference in performance to something in a clear way, not just compare models which are different in everything. Otherwise, we don't know why one is better than another. Now, it's very common nowadays to use machine learning models. And with machine learning models, hypothesis testing is much more difficult because these models are much more complex. So, but it's not impossible. It's not impossible. And here it's a paper from Peter Reichard, came out in 2024, which uses this concept of metamorphic testing in order to test whether machine learning models they are doing the right things, let's say for the right reasons. But for example, we know that if we have more rainfall, we should expect more stream flow. Okay, and we know also that if we have more temperature, if we increase the temperature, we should expect less stream flow. So what we could do is to test whether the models behave according to these principles that are, let's say, that everybody would agree upon. So, and this is what we did. So there are two conceptual models, the GR4J and HPV. And indeed, if you increase the rainfall, the stream flow increases for the conceptual models and also for the STM models. Whereas for when we increase the temperature, something different happens. So for the conceptual model, if we increase the temperature, we have less water. But for the LSTM, in some cases, we have more water. And so this behavior of the model, which is in contrast to expectations, this could help us accept or reject different models. Okay, so arrived to some key messages from this presentation. Well, focus, so if we want to improve model predictions, we should probably invest less on improving the models and more on data and extracting information from data. There is probably a lot to gain from exploring ways to extract information from landscape data, because there is a lot in these maps that we are not using. There is this issue of regional relationships, so relationships that may not be applicable everywhere. And so regional analysis, therefore, are important to discover these regional relationships. And then, if there is perhaps not much to gain in, let's say, improving models for better performance, I think there is still a lot to gain in using models for learning the catchment behavior. But in order to do that, we need to follow some guiding principles. Otherwise, we just compare models and we don't learn anything. And yeah, with this, I think is everything from my side.
Thank you, Fabrizio, for your presentation. I think we might have some questions and time for if we have any in the audience. Maybe I can start with, okay, Chris.
Yeah, I mean, I was wondering, how did you make the clusters for the geological maps?
Yes. So at the moment, these clusters, the way we did it was just based on, let's say, expert knowledge, experimental understanding. So, for example, we know that sandstone is probably a permeable rock,
Yeah.
and maybe plutonic rock is less permeable. No, so this you can somehow rank them in relative permeability classes. We know that clay is not permeable. We know that other types of rock like that can be fractured, can be more permeable. So this was based on, let's say, expert knowledge. Probably there are other ways of doing it. If you have a lot of data of catchments and you assume that geology should control base flow, then you can think of ways to cluster this in such a way that they give you the best fit to the base flow, and then reason afterwards whether this classification is reasonable or not. But let's say we did it a priori based on experimental understanding.
But the classification seems to work pretty well, right?
But in this case, it worked well. But when we then went to other catchments, we found out that basically there is a lot of variability. So if
Depends
you
on
use
the
the same
case.
classification in other catchments, then we find that doesn't work well everywhere. Actually, in other catchments, geology doesn't seem to matter much, at least classified in this way.
Fox and me.
Okay. Slovenia?
Yes, thanks Fabrizio for the nice talk.
Mm,
I really like the idea of that having no data sometimes can be better than having data.
All right.
And I was wondering, like, yeah, if you say we need better landscape data, so if you could wish for data or could say you could improve some data, do you have like some data which you say, okay, this would be really, really important for our stream flow modeling? So is there like one or two variables which you say like, okay, this is really something we would need?
For example, one data that type that is supposed to be very important but is very difficult to get is soil depth. Soil depth is really something. But on the other hand, I have no idea how this could be actually measured in a reasonable way, in a pragmatic way. So all models require this, but there is very uncertain knowledge about soil depths.
That's true, but maybe we can still wish for it. Maybe some
Yeah, we can wish.
miracle methods will happen. We
Yes.
never know. Thanks.
Are there any other question? Chris?
Yeah, it's related to Svenia's one. But maybe some experimental catchments at the catchments in Luxembourg, they might have this kind of data. I was surprised that before 2000 the data was not shared and so on. Maybe I am old, but not
because
so
you
old.
are young, because you are very young. This is for people that, yes, older than 30. Not you.
Yeah, I'm 44.
Yeah, but it really
experimental
was,
catchments have them, right?
it really was like that in the past. The models and data were difficult to get, and people didn't really see an advantage in sharing them because it was an advantage for them to have them. It's something relative. It's a new development in science. The fact that data and model codes are shared.
But these experimental catchments, maybe they have how to measure. I mean, you were working in Luxembourg for a long time, so these catchments have they take measurements of the soil depth or
The soil depth. Let's say they only hope to have some reasonable estimations is on really experimental catchments where geostatistical analysis are feasible. So where really you can do detailed field work. But if you look at let's say Moser catchment, 27,000 square kilometers, then this is very difficult.
and maybe you can share at some point the link to the people share or look the link to eStreams, the website that you already have developed with Tiao.
Yeah, the eStreams.
And maybe I can ask a question based on this figure. I think what is also still challenging, the poorly gauged catchments are still poorly shared.
Sorry, there?
The poorly gauged catchments are still poorly shared. Like,
yes.
I'm from Turkey, for example. We don't have much more rain stream flow observations. I mean, we have, and some of them are open, but not maybe in some friendly way. So the question might be the data could be somehow still challenging in some parts. And what do you think about these regions?
It is a problem. Some regions are much better represented than others. And it's then difficult to understand how things. Well, these analyses are obviously that require data are only feasible in regions that have sufficient that are sufficiently represented. So there are engaged catchments that are really engaged, for which you cannot even test your ability to predict in engaged catchments. We can only test the ability to predict in engaged catchments, actually. That's the problem.
Yeah, we still need maybe some hypothesis to bridge poorly gauged and rich gauged catchments to make a connection or some methods.
Actually, probably, yes, we should maybe think of studies that use much coarser data, much coarser data, pretending that we don't have data maybe also in the engaged catchments, and then see how reliable would be this prediction in such cases, just to have an idea of how reliable they are in the really engaged catchments.
And I also want to add this. It's also important from your slides that not all data is good for all analysis, and the resolution of the data matters a lot. And sometimes people have a feeling that they have a lot of data, they have a lot of models, so they might end up with garbage in, garbage out conclusions. So I think your key point is valuable to draw attention about the conclusions we are extracting from the models and data?
Yeah, sure. So unfortunately, what comes out of this analysis is that sometimes it's better not to have. So if you have data, you might think you are adding information to your problem, but sometimes you are not. And it is very tempting to say, no, yeah, I had this data without no, and if you don't know that it's bad data, no, you might think you might come to some conclusions, such as, for example, that a certain landscape attribute doesn't matter just because it's poorly represented. This is a really difficult problems, no? Sure. Therefore, as you said, if you have garbage in, you get garbage out of your analysis.
And just as follow-up question from this slide, are you thinking to make some kind of analysis or catalog about data quality, because of all the CAMELS papers and data sets are about getting data, but they don't analyze the data quality, right?
All this, well, I think there is, they specify also the quality of the data, many of these hydrological databases. So whether it's reliable or what is the level of uncertainty of this data. In addition to that, these hydrological databases often make extra analysis to figure out if there is some obvious mistake with the data, such as, for example, if you have runoff coefficients larger than 1, then the catchments are flagged in some particular way. And this is certainly the case for streams. Perhaps Tiago can say something about it if he is there.
Oh yes, definitely. I don't know if I have anything to add, but yeah, this part of the quality is very important, and even more now when you make more and more data available, and how in these large sample studies, regional models, should I add this new data, this new time series, or should I not add it? It's very important and very still very persistent problem.
Thank you. Any more questions? Or maybe we can close the session if you don't have. Okay, thank you,
And then thanks a
Fabrizio.
lot for inviting me for this presentation. It was nice to share what I'm doing and with you, and I hope that